NVIDIA just quietly dropped something that changes how AI agents are trained, and the research world is still processing what this actually means. We're talking about ProRL Agent, a new open source system that nearly doubled the performance of a small 8 billion parameter model on one of the hardest real world coding benchmarks out there. It did this without making the model bigger, without adding more training data. It just fixed the way the training system itself was built. And the crazy part is, the old way everyone was doing this was silently burning hardware resources this whole time, and nobody fully stopped to fix it until now. So let's talk about it. Alright, let me set the scene first, because the problem this is solving is one of those things that seems obvious once someone points it out. When you train an AI agent, you are doing two very different jobs at the same time. The first job is running the agent through real tasks. Think of a coding agent exploring a code folder, calling tools, writing and testing code, and figuring out what went wrong. That whole process, researchers call it a rollout. It is input and output heavy. Lots of file reading, lots of waiting for tools to respond, lots of back and forth between the agent and the environment. The second job is the actual learning stage, where the system looks at everything the agent did and adjusts the model's weights to make it smarter next time. That part runs almost entirely on the GPU, doing heavy math, moving gradients around, and syncing across multiple machines. Here is the thing. Those two jobs hate each other. The first, they fight over the same resources, and in almost every system that existed before ProRL Agent, both jobs were locked together inside the same process. You could not run one without the other. So while the GPU was waiting on a tool to finish executing, it just sat there doing nothing. And while the model was learning, new rollouts had to wait their turn. The whole pipeline was one big traffic jam, and everyone just accepted it as a cost of doing business. NVIDIA looked at that and said no. ProRL Agent pulls the rollout system completely out of the training loop and turns it into its own standalone service. The trainer sends a request through an API, the rollout service handles everything, and the results come back when they are ready. The trainer does not care how the rollouts happen or what environment they run in. It just gets the data it needs and keeps training. That separation is the core of the whole design, and it sounds simple, but the impact is massive. Now, here is where it gets interesting when you look at what that separation actually unlocks. NVIDIA built what they call a three-stage pipeline inside the rollout service. The first stage is the setup stage, where worker processes spin up the sandbox environments, get the tools ready, and configure everything the agent needs. The second stage is the actual running stage, where the agent goes through the task step by step and collects its trajectory, meaning every action it took and every result it got back. The third stage is the evaluation stage, where the system scores the agent's work and turns that into a reward signal the trainer can use. The clever part is that all three stages run at the same time for different jobs. While one job is being evaluated, another is already running, and another is still sitting up. Nothing waits for anything else. It is like a proper factory floor instead of one person doing every step of every product one at a time. And they did not stop there. NVIDIA noticed that a huge chunk of time in every rollout was being eaten up by basic tool operations. Things like running a shell command or executing Python code. These are the most common actions a coding agent takes, and they were running slower than they needed to be. So the team went in and replaced the tool backends at a very low level. The old way of running shell commands inside the sandbox used something called tmux, which is a terminal multiplexer that adds a layer of overhead every single time. NVIDIA swapped that out for a PT process-based direct pseudo-terminal. PT process being a Python library that connects directly to a own process without the extra layer tmux adds. And shell command time dropped from 0.78 seconds to 0.42 seconds. That is almost cutting it in half. For Python execution, they connected directly to persistent kernels using an in-process method instead of going through a network gateway. They also replaced the network protocol used inside containers with Unix domain sockets, which are faster for communication that stay on the same machine. Each one of these changes sounds small on its own, but multiply them across thousands of agent steps per training run and the settings compound fast. There is one more technical detail that people in the ML community found genuinely interesting, and that is what NVIDIA calls the token in, token out approach. Here is the problem it solves. When the agent generates a sequence of text during a rollout, that text is represented internally as a list of numbers called token IDs. The issue is that when you save that text and then try to reread it during the training step, the system sometimes ends up with slightly different token IDs because of how text is split and processed again. Even tiny differences here can mess up what the model learns. NVIDIA fixed this by never converting the token IDs back to text in the first place. The raw token IDs travel from the rollout service directly into the training update, unchanged. It sounds like a small detail, but it removes a real source of noise that was quietly hurting training quality in other systems. Now, let's talk about what all of this actually produced in practice. Because the numbers from the SWE-Bench Verified benchmark tell a clear story. SWE-Bench is one of the most respected tests in the AI agent world right now. It gives agents real GitHub issues from real software projects and asks them to write the code that fixes that problem. No hints, no shortcuts, just the agent working through a real code base the way a human engineer would. Queen 3.8b went from a baseline score of 9.6 all the way to 18.0. That is nearly double. Queen 3.14b went from 15.4 to 23.6, which is notable because the paper itself points out that the previous best published result for a 14 billion parameter model on the same benchmark, ProRL Agent 14b v0, was 21.6. ProRL Agent pushed past that. And to be clear, these improvements came entirely from the training infrastructure. The models themselves did not change. No new architecture, no more data, just a better way to run training pipeline. The scalability results matter just as much as the accuracy numbers. NVIDIA reported that rollout throughput scales nearly in a straight line as you add more compute nodes. In the world of distributed training, that is actually hard to achieve. Every time you add more machines, you usually hit new coordination problems that eat into the gains. The fact that rollout throughput keeps climbing at a near linear rate means the architecture is genuinely removing the bottleneck rather than just moving it somewhere else. For companies training large agents across dozens or hundreds of GPUs, that kind of scaling is a big deal. In fairness, there are real limits here worth knowing about. ProRL Agent was tested specifically on software engineering tasks. The team showed promise in STEM, math, and general coding, as well with steady reward growth during training across those areas. But the headline benchmark results are focused on SWE-Bench. The system also currently uses Singularity containers for its sandboxes instead of Docker, which works well on shared research computing clusters but may require adjustment for other environments. And ProRL Agent is a training infrastructure tool, not a finished agent product. You still need to bring your own model, your own training setup, and connect everything yourself. It is an open source building block, not a plug and play solution. That is where we will wrap it up. The real question now is how quickly this design shows up in the workflows of teams building serious agentic systems, and whether the rest of the field adopts the same separation. Drop your thoughts below. Make sure you are subscribed, hit the like button, and I will see you in the next one.